Generally speaking, we always feel as though we're the ones who receive all the phone calls and with all the questions and have to have all the answers for everything. So what I'm going to do is try to give a little insight into some of the thinking that goes on with regard to how we look at designing buildings and specifically towards the net zero energy goal. Energy consumption and how it can be reduced in our everyday lives has become a critical issue today, obviously. Significant amounts are required to maintain a comfortable indoor and sometimes even outdoor environment. Approximately 75% of direct use electricity is used in our residential and commercial buildings. 55 to 60% of this amount is used to simply maintain a habitable, comfortable environment, heating, cooling, ventilation, and lighting. Up until very recently, the energy source always came from outside the building itself. The last 20 years have trended towards reducing energy usage in commercial and residential structures, and this trend is very much accelerating, as you've seen previously in some of the charts. It is not necessarily, I believe, accelerating due to technological advancements in equipment, but is progressing exponentially due to the information technology available to collect and analyze data, pointing out issues more clearly. This, in turn, has provided the impetus to develop high-performance products and identify design approaches for use in our built environment. Technology did initially make this possible by pushing the envelope in the development of new products that perform better. This has its roots in all of the scientific research and development activities in labs, the Department of Energy, as an example, manufacturing facilities, and some commercial development. From these origins, things eventually find their way to where we are, the single-family home. It is not easy and seems to become more complicated year after year, but it's not difficult either. Many principles are already inherent in good design practice. The goal, the net zero energy building, is the subject for us. For my part, I'd like to describe a path towards this goal and present thoughts and ideas that can make it incrementally easier to get within reach of the zero in the energy ratings index. By definition, the net zero energy building includes an on-site renewable energy supply, but the focus that we will have here is about using tools available as part of the design process that will allow us to minimize the quantitative need for these add-ons, thereby lessening the cost burden and complexity of the total project. Energy codes have found their way into every aspect of the design profession and construction industry. Requirements are prescribed for everything now, from raw materials to finished products and equipment. Labeling is pervasive. To me, in the time that I've been doing this, it's a curious diversion, as traditionally the role of codes has been to establish parameters for the structure and life safety of building occupants. At the same time, this kind of tells us that our approach to designing buildings has fallen way short and gotten very sloppy when it comes to efficiency and planning. For the commercial or residential building, the establishment of where it is located, its climate zone, sets baseline criteria for the next three items that you see: the building envelope, lighting and power, and mechanical system efficiency. These categories are loaded with specifications and prescriptive requirements that can be difficult to wrap your arms around in a manner that allows everyone to understand the interrelationships between these systems. Commonly referred to as the whole building approach, it is exactly these relationships that need considered when we propose to build and occupy a building. Which leads us to the question of how, with all of this data being translated into code requirements, can we most efficiently determine the best approach to make a building of any type that provides an innovative design while using less and less energy? I have the bottom two, which those of you in the back may not be able to read, but item 5 is noted as energy modeling versus prescriptive, and item 6 is passive design considerations. With tools available to us now, which are getting better and more understandable year after year, we can determine within a narrow range of probability the effects of decisions made on a multitude of fronts that tell us how a building will perform. We can on the fly comparatively analyze system components to determine the most economical trade-offs. Energy modeling tools can set our sights on the zero energy goal early in the project and provide solid information for decision making. It is becoming more common to use modeling, examples of which we will get into later. However, it is predominantly an alternative currently to figuring your way through the requirements of a prescriptive approach. However, to us, the real power lies in its use to making informed decisions throughout the design process for any type of project. The second approach, which should actually be the first consideration for any project, simply involves making smart decisions about fundamentals such as siting, location and area of windows, wall composition, etc., commonly called passive design. It should not be seen as a style, label, or trend, but something quietly inherent in any building. In this area, such considerations go as far back as the dwellings of the Native Americans. Oops. I think it's important to understand where all this has come from. We originally became involved in energy, concerns for energy use in the late 90s when it was in its infancy. We worked on a pilot project, one of a half a dozen or so, that had a goal of trying to reduce energy usage, and basically this had to do with mechanical and electrical systems. The items that we had to deal with are very similar, in fact they're the same as the items that were on the previous slide that we're currently using to design our energy reducing components of buildings. Things like insulation, lighting, the mechanical system, how the fenestration works, daylight transmittance, and at that point system commissioning. When that project was undertaken, we were very, very much at the time in the late 90s kind of winging it. There was software that the Department of Energy had developed for energy analysis so that you could use during the course of design, DO2 it's commonly called, and for this particular project, the level of sophistication of this available information was pretty minimal at the point where we were just fundamentally using basic calculations as to where the sun was in the winter and where the sun was in the summer to try to determine the best location for fenestration in the building and the size of the fenestration and so on. What you see identified as daylight zone A, B, and C was an early attempt at lighting controls, daylight lighting controls, where now we are using occupancy sensors to be able to recognize when someone is in a room and what level of lighting should be on. At this point, we literally had switches on the wall that were, if it was a nice sunny day, daylight zone A didn't need any light, so you relied on someone to turn the switch on and off in order to control the amount of light required. The other interesting aspect is at that point, we really were working under two, not codes, but guidelines that were beginning to be in place. At that time, ASHRAE 1989 was the kind of rule, and even LEED was was just in its infancy and hadn't really been developed. So all these things were just really kicking off at that point, but the concerns were there, and clearly we were moving in that direction. And this is where we are now. And I could probably throw 3 or 4 more slides on here that list countless other guidelines, procedures, codes that you have to consider, and that's what, and we, as a design professional, have to consider when we are designing buildings. It can be somewhat mind-boggling when you look at it. And it's very quickly moving. The ASHRAE went from 2007 to 2010 to 2013 to 2016, and all of these at all of these points, they increased the requirements for energy efficiency reductions. You get to the International Energy Conservation Code, which 2012 was now replaced by 2015, and 2018 is about to come out. And so you can kind of get the sense that these things are at times difficult to kind of keep up with. All of this is pointing towards the goal of this energy rating index compliance, which has been spoken to previously, where we have this 0 to 100 list index, and you have to design to a certain level of criteria, and this will vary from state to state, municipalities, and so on. Some will require that you design to a 57 rating, a 54 rating, and things. So it all can kind of can be a little bit, complicated. Where is Arizona in all of this? Arizona, as you see here, is the maroon color, and these are all the 50 states. The adoption of codes and dealing with energy efficiency go from the lowest, which is the one on the left, and then Arizona currently uses it's aspirate 90.1 2007, and then the dark green ones are all the way up to 2013. So currently that's where Arizona stands in terms of specific requirements of what you need to follow. However, Arizona is a home rule state, and that meaning, as you know probably all too well, that every municipality, county, you name it, can adopt certain aspects of a particular code. In Yavapai County, which is what you see, the chart on the two columns on the left with the climate zone 2, 3, 4, these are the requirements that you are to follow when you're designing a building in Yavapai County with regard to various R value, U factor, glazing fenestration, solar heat gain requirements. And on top of that, Yavapai County splits itself into two, where if you're below 3,500 feet as an elevation, you adhere to a certain set of requirements that you see in the red on the right column. Whereas if you're above 3,500 feet, you adhere to another set of requirements. You can go on, and Camp Verde currently uses the IECC 2012 version, Clarkdale's 2006, Prescott 2012. It just goes, it shows you the complexity of things that you have to deal with in terms of meeting all of these data points, when you're designing a building. Currently, the two columns on the right are the current IECC 2015 requirements, and that shows you the difference between the commercial side and the residential side. And what you can notice there, if you start going all the way from left to right, you see increases for the most part in requirements for performance of all of these components, of your building. And now 2018 is about to come out, and I can tell you that it's going to take the requirements from 2015 and kick those up a notch or down a notch, as well. It's all just headed in that direction. A couple of the interesting points that have come up that I have highlighted in boxes there. The R for a wood frame wall R value following across that horizontal line. The commercial side is an R13 plus an R3.8 CI. It was brought up a little bit earlier with regard to this specific requirement, and that means continuous insulation. The trend now is that you need to have your building envelope insulated all the way around with no breaks. The prior code, 2012, actually allowed you to have a 5%. But you have to prove by calculation that you had that you were not exceeding having a thermal break by more than 5%, around the envelope of your building, and so this is now, moving in that direction. This is the whole building approach, which ultimately is what we're supposed to be talking about here. Everything, the whole building approach, the fundamental definition is the idea that all systems are interconnected, having to do with water usage, having to do with fenestration, orientation of the building, the potential to reuse water, to exchange heat, as was mentioned, in order to kind of just conserve, and begin to reduce the energy use, you know, in your building. These two examples are basically probably two of the primary issues that are facing us today with regard to the design of buildings, having to do with how the envelope is sealed and how it prevents heat and air vapor penetration around the envelope. I think Tanner had previously showed a slide similar to this, where this is your typical wall of your floor slab on grade or whatever it might be, which is not insulated, and tremendous amounts of energy, heat, energy, or cool air, you know, it doesn't really matter, escape through that. That's a typical wall construction where you have the heat transfer going from outside to inside because you do not have the break, you do not have the sealing of that cavity or whatever it might be. What you're looking at here is an example of what is done through energy modeling. And I'll show you later on why I think things really are trending more in that direction, and we're very, very big proponents of it. Down here you have the same example in terms of the potential for heat or, you know, hot air or cool air, just things escaping because of the difficulties of making these junctures sealed up and having a completely thermal envelope. This is a part of an analysis that is done as part of an energy modeling program, whereby you are looking at a wall system. The dark red is insulation, and what you see here is, you know, in this diagram, the transfer of heat and in the solid line, and the transfer of air vapor in the dashed line, and the requirement that everything stay to the outside. It needs to stay to the outside of the building, you know, outside of the, you know, the surface that you occupy. This is another example of a similar situation, except that if you note here, this shows a non-continuous insulation condition. This one is the latest. Actually, this is a brand new building that we're just starting construction on, meeting the new code requirement for a continuous thermal and vapor barrier. That connection of the vertical wall insulation has to physically connect with the roof insulation to form a continuous envelope. And you would see down at the bottom the same thing is happening. We're getting to the point where, and I'll show you a little bit later, where we're being asked to insulate the entire floor slab because the floor and the earth are different temperatures. But those are things that are evolving. This is an example of what I would call reverse energy model. It's common in residential construction, sometimes not so much in commercial construction, but it's a very, very important issue in that when a residential building is done, it's common that a contractor will take what we call a performance-based specification and have to engineer and determine and size the equipment for heating, cooling, hot water heating, and everything in order to basically meet what he's being given. So what happens is that you start taking all the components of the building for heating and cooling, the square footages, there's something about orientation and things, and you put in all these numbers and it starts spitting out information about how big your air conditioning unit has to be. And then there are graphs like so that show you how things are going to perform. Like as an example here, this is showing that we are not meeting the requirements. We're exceeding the amount of glazing that's permissible under the prescriptive code for this particular project. But through the use of this energy modeling, it's proven out that everything is okay, because even though we've crossed this line, when you start looking at what's below the line and what's above the line, the average is that you're meeting the conditions. This is all energy modeling. It's all fundamental stuff, and most builders, contractors, will use this, and some of it's available free. I mean, some of it you have to purchase, but it just depends on how sophisticated you want to be. To us, what we see is that this type of technology is better applied at the very, very beginning and throughout the project, so that you can understand as you're moving through the project what works, what doesn't work, what it's ultimately going to cost you in energy consumption and building cost, in the final analysis. This drawing here, this is an example for us to get to something like this. This is an example of this is a building, and all that's depicted here, what's solid and what the makeup of the wall is, what's a glass, what's the different types of glass, the different types. This is a metal panel system, this is a precast concrete system. All of this is represented in square footages, and it has its U value and its R value and its makeup, and all of that is plugged into the system. So we could examine, as an example, if this was a solid wall versus a glass wall, what impact that little bit might have on what you're doing energy-wise. There are a number of systems that things available. We use CAD. We use AutoCAD. AutoCAD has other programs that work seamlessly with it that analyze and provide that data. It's just an add-on application. The DO2 software is the final end analysis of that. It provides that information, and all of these things are beginning to be more and more seamlessly integrated, so you can use all these systems together. This also has to do with 3D modeling. If you do the project in CAD, it's not as easy as I'm just saying you click a mouse and you have a 3D, what's called a Revit model or a BIM model, but it's not that far from being the case. With all of that information, it tells you everything that you know about the building. How thick the insulation is, how thick you need it to be, the type of glazing, the U value, all of that. It kind of solves the problem for you, which for us is it's kind of more interesting than the prescriptive approach of going through all the boxes and making sure that your data is all in line, and you meet with the code official and he says, oh, you're good to go. Okay. This is that same project, but just what the impact is on using that type of way of looking at the design. You deal with insulation, whether in this case it's continuous in terms of it wrapping up and over as opposed to breaking, the type and thickness, the amount of daylight penetration gets analyzed. These are sunshades that that determine based on the orientation of the building how much daylight's getting in, how much is being blocked, eliminating solar heat gain. Of course, high performance windows, low E glass is it's kind of a must these days. Then the building wrap and vapor barrier. This is an example here where the insulation is continuous under the slab. There is a problem right here in terms of the break, that break happening, but the insulation, when you analyze it and you see the travel of the heat and cool air, by the energy model, it proves to work out. This example here, what you're seeing, that you saw it at the very beginning slide, this is a classroom. It's a pre-K center. But this classroom, the lights are on literally because the sun is shading that. The lights in the adjacent classroom are off because of the daylight penetration and the building occupancy. And all of that works residentially as well, quite honestly. The passive design aspect, this drawing is probably one of my favorite drawings. This used to be a Google Earth app where this project happens to be my house in the foothills of Mingus Mountain, is put on the site. It's located longitudinally and latitudinally, and this drawing tells you where the sun is every hour of every day of every month of the year. So using this tools such as this, you know where and how to orient your building, the amount of glass, if you use glass in a large surface way, the need for overhangs, the need to be able to prevent direct sun into the interiors of the building. This happens to be a result of that study. This plan is, there's the sun. The overhangs here by calculation vary from 2 feet to 6 feet, just because, as the sun travels around, that's a 6-foot overhang. This tree, where your site is, the landscape around it, the tree solves tremendous problems because it provides shade, prevents the solar heat gain. So all of this is done by virtue of that calculation. So in the end, these are our issues that we have to deal with, and they are getting more and more important, and the criteria to resolve them is getting more and more, it's getting, it's more complicated. There's a lot of information out there to sort through and things, and you do this, you have to be aware of what's going on with all of these things. But for us, what you start to see in terms of some fundamental aspects about your building, the elements of passive design are very, very critical to kind of get you going right. And then I think energy modeling is really becoming, or will become, just a standard way of looking at how you do buildings, both residential and commercial. It's already being done pretty much. Unfortunately, someone bought that app. Yeah, if you Google, Google, they have thousands of apps and things. And one time we stumbled on that, and all of a sudden you knew where the sun was all constantly. A couple of years ago, some third-party company bought it, and now it's for sale. Right? I mean, all that stuff's for free, but you can still, if you just probe around, you can find things that will help you with all of these aspects.